It's my pleasure to introduce Dr. Long Song, who's had a very interesting journey into academia. Started off as a physicist and then did a PhD in computer science and has worked in wheat genomics and now doing things to do with hospital stays as he's joined the University of Melbourne recently. Anyway, we look forward to hearing what you have to talk about. Thank you, Long. Take it away.
Thank you, Peter, for introducing me. Thank you, everyone, for joining the seminar. The presentation title is Developing Interpretable Machine Learning Models to Predict Length of Stay and Disposition Decision in Emergency Departments. This presentation is about using machine learning technologies to analyze data from real world. So it includes four parts. Mainly I'll focus on data analysis workflow, this part, second part. So emergency departments operate under substantial pressure globally. I've ever been to emergency department once. I took a taxi to an emergency department and I wait about 10 minutes in the waiting room, and one nurse did admin work with me. Then I wait for another 20 minutes. Triage nurse did a triage with me to do the initial assess of my problem, a small problem. Then I waited about more than 1 hour. Finally, I was introduced into the department. A doctor checked me and did some checks. Then I wait for another 2 hours to do another check, and wait another 2 hours to be finally to be discharged. Most time wasted for waiting because doctors and nurses are were very busy. So for patients, the waiting time is very long and it's very crowded within the emergency department. So all this affect patients' satisfaction or outcomes. In 2011, Australia introduced National Emergency Access Target (NEAT) to want to ensure 90% of all patients, whether discharged or admitted, can leave the emergency department within a 4-hour time frame. However, till now in Victoria, only 54% patients can meet the target. So there was still a very large gap. In fact, finally, this target was dropped later because it's impossible to reach this target. Now, machine learning can help. So in hospital, all hospitals use EHR system. This stores and manages patients' medical information, health history, treatment plans, medications, many kinds of data. Machine learning models can be developed with data sourced from EHR. So emergency department doctors and nurses can use machine learning models to facilitate earlier and better disposition decisions. So for instance, in this project, so we try to develop machine learning models to predict 4 outcomes. Length of stay, so the patient, how long the patient will stay in emergency department or in hospital. So the time, so it can be defined in 2 ways. One is a binary length of stay, so less than 4 hours or greater than 4 hours. The trinary length of stay, less than 4 hours, between 4 hours and 24 hours, or greater than 24 hours. The second kind of outcomes is discharge disposition. So binary discharge disposition is a discharge or stay. Trinary is a discharge, short stay, or admitted or transferred to another hospital. And the predictions should be done at 3 different time points. So at 10 minutes, 60 minutes, or 120 minutes from the end of triage, the triage nurse does the initial assessment of the patient to decide whether it's very urgent or is not that urgent. So at 10 minutes, so some information available. For instance, the triage nurse input some information, and the 60 minutes, normally the patient has been seen by a doctor, and 120 minutes, more investigation or observation have been done. So we need to predict 4 kinds of outcomes at 3 different time points. So altogether, we need to develop 12 machine learning models. But there were a lot of challenges. So first, the data from real world is very complicated, which means the data analysis is also very complicated. Secondly, for this project, within a clinical environment, machine learning models must be interpretable, which means black box models are not acceptable, like deep learning, XGBoost, etc., all not acceptable for this project. Third one, the data analysis framework must be transparent because when a model trained at one hospital is applied at another, its performance significantly decreased. The reason is every hospital, every emergency department has its own operating procedures, etc., etc. So, and they may do different check. I mean, measure different features for the patient. Anyway, so the data analysis framework should be easy to be adapted by other hospitals. So some existing studies, so I listed 3. So these studies also predict binary DD at 3 different time points and use logistic regression, use 43 parameters. It got a very high AUC, which is doubtful. And some other studies predict binary length of stay, use KN model. This is not interpretable model. Use only 6 parameters. So this AUC is not that good. And study 3 do a lot of predictions and use XGBoost. The issues with these studies is data processing are not clear or have some problems. And some models are not transparent, I mean, not interpretable. And some results are doubtful. So let's look at the data analysis workflow. So normally, and this is a typical data analysis workflow for analyzing data, for modeling and prediction with real data. So we got raw data. And at the beginning, we split into modeling data and testing data. And modeling data and testing data separately do data extraction, data preprocessing, data processing, the imputation. And for modeling data, we develop models. Also, feature selection was done on modeling data side. Testing data, finally, we apply models to testing data to validate the models and the visualization reports. Also, cross-validation should be done on modeling data side, but not here, not illustrated here. And often there was some data leakage during this workflow. So for testing data, should never be used on modeling procedures. So, but information can be used by testing data from modeling data. I mean, so this arrow direction. Also, for testing data, the outcome target column should not be used before validation. So let's see this one. This presentation is mainly focused on the real world data analyzing. So let's see. So the first step is raw data analysis and create dictionaries. So this is raw data. This data was extracted from the hospital's operating system and by hospital data scientist. So it gave me very large files, which means the data analysis can be only done on HPC, not on personal computers, very large data. And some file just a table, so each emergency ED visit one row. But some, like this one, flow sheet, is different. So one patient during one visit can have many measures, and each kind of measure can be done many times, like a blood pressure, measured many times. So at a different time, so has different values. So this is raw data. Raw data analysis, why we need to do raw data analysis? Because the most important thing is the raw data was extracted from the EHR system. However, often, very often, there were serious issues with raw data. So if we don't check the raw data, something was wrong, and later we found something was wrong. A lot of time wasted. In fact, during this data analysis, 3 times I found there were serious issues, and I reported back, and the data scientist from hospital extracted the data again for me. And each time, they spent more than 1 month to extract new data for me. So if we don't check the issues and later found issues, then a lot of things need to be done again. Also, raw data need to be summarized. For instance, this column, this feature is disposition decisions. We said we need a binary outcome, but this feature has more than 20 outcomes. So we need to merge this 20 class. So we need to merge these 24 values into 3 or 2 class. And some results need to be generated for later data analysis. And finally, we need to split the raw data into modeling data and test data. Dictionary. Dictionary is very, very important. If you ask ChatGPT, dictionary is very important in medical data analysis. Yes, it's very important. However, the data scientists from hospital, they don't have dictionary. So I need to create dictionary myself. So I create this dictionary and I searched every feature's meaning and guide to use and explanation and confirm with the clinicians they are correct or not. We can't do data analysis without understanding data. If we don't understand data, many, many mistakes will be made and the result won't be good. So it took time to create this one. Then data extraction. So this is the modeling data. So split raw data into modeling data and testing data. So this is modeling data. And data extraction, we need to extract data from all these files to create a big table like this one. And during this procedure, some features are not needed. And the doctors told me some features definitely not needed. And some features has incorrect values. So how do I know the values are incorrect? I need to check dictionaries. And some medical features need to be processed, like merge values, outcome, or other features. Some value need to be merged into one. Yeah, and some new features need to be created, like diagnosis count, problem count, etc. Finally, from the raw data, after data extraction, we get a big table like this one. So for instance, during this data extraction, we create a feature problem count. There's a feature, ICD-10 code. This feature is very good. It's about the disease classification or symptom classification. However, this feature is a categorical feature. It has more than 87,000 possible values. 87,000 possible values. It will be very difficult to use this feature. So I decided not to use this feature. Instead, I create a new feature, problem count. This problem count to count the active problems of the patient before this ED visit, because we can only use information prior to the predicting time point. However, the problem found during this ED visit not recorded time. So I don't know whether the problem was found before 120 minutes or after 120 minutes. So only problem count before this ED visit previously can be count. So this is the one example of create new feature. And the data preprocessing. So we get a new big table, including everything we need. Because a different time point has a different data. So for different time point, we need to filter medical data. So 120 minutes has more data, 10 minutes, 6 minutes has less data. And outcome columns need to be created, binary outcomes, trinary outcomes, and length of stay, and a disposition decision. And some columns need to be processed or removed. Because categorical features, some categorical columns has many values. So in this data analysis, values more than 50 were removed for those columns. Finally, triage comments. This is a free text comments. So free text processing is also difficult. So in this data analysis, we just search some keywords to convert free text triage comments into potential issue, just several. And these several issues can be combined. Finally, these triage comments convert into categorical feature. So now data processing. So we have a table for different, we have one table for different time point. So some feature has very high missing rates, so removed. And some category feature values still need to merged. And we need to process outliers, imputation, categorical features, and the numerical features. So let's see. For imputation, because it's a very big table, if we try to use some algorithm like a KNN, the imputation time would be very slow. For instance, more than 7 days. It's not acceptable. 7 days is too long because I need to do many testing, and so this way is not acceptable. So let's say a categorical feature. For instance, this feature inserted into the location of infusion. So for instance, arm, hand, wrist, and there's a missing this field, no value. Some class only appear a few times, like a hand, many forearms. So let's say the solution in this data analysis is like this. So first we count how many for each class, and then calculate the how many for each class when length of stay more than 4 hours. So check the association. So the probability for each class, for instance, let's say this one, hand. There were more than 10,000 hand value in this feature, and about 9,700 has length of stay more than 4 hours. So the probability of LS greater than 4 hours is 0.91. And I use logit function to convert this probability to this, get this value. For missing, we treat it as a distinct class, not impute missing from all these existing values. There's a reason, because missing not, in fact, because the patient doesn't need infusion. So the missing is not because some values are missing, because the patient doesn't need infusion. So there's no value for this one. If we check the probability of missing, it's only 0.45. So if we try to impute the missing value with all these values, definitely is wrong. So we treat it as a distinct class. And so we also calculate probability. So for this feature, we convert all these category values into logit probability as numerical values. For numerical features, for instance, this one is systolic BP, blood pressure, and this is density plot, and this is the probability association plot. We can see very low blood pressure and very high blood pressure are not good. Length of stay will be more than 4 hours. In the middle, the length of stay is much lower, the probability. So we know generic linear models cannot cope well with this kind of U-shape correlation with the outcome. Also, there are missing values, and there are a few outliers. So we use a new method to process these kind numerical features. So we segment the feature values into 25 intervals. So like this one. So missing as a distinct interval, and the values less than 101 as one segment. Then count the values and count the length of stay more than 4 hours, calculate the probability and logit probability. We can also find missing values logit probability is very different from all others. So which means if we try to impute the missing values with existing values, definitely is wrong. So from this way, although the numerical values, we still do processing to get another kind of numerical values. Also, outliers will be in the first segment or the last segment. So outlier also processed. Missing value processed, outlier processed, and the U-shape correlation processed. Because there are hundreds of features in the real data system, and most about half features were not used from the advice of the doctors, but still there are not. For instance, there are 68 features after data processing. 68 features too many for building models. So we have one-step feature selection before modeling. So clinician told me that age, pulse, and systolic BP are considered essential based on domain knowledge. Then we use Nassau regression for feature selection. So Nassau regression can reduce the number of features automatically. So we use Nassau regression to build models, then get the importance of the features And finally, so the number of features automatically reduced to 49. But 49 is still too many. So finally, we select top 18 most important features together with these three. So altogether 21 features selected. This is a panelized logistic regression, so ridge or elastic formula and object function. So do modeling. So 4 outcomes, 3 prediction time points. We tried 8 models. Logistic ridge, NASA, elastic lag, decision tree, random forest, SVC, and ensemble. And we do cross-validation testing. Different models, speed is different. All this done, always running on HPC. So some models modeling just 30 minutes to several minutes to 30 minutes, but SVC ensemble 2 to 7 days. This is not acceptable. And finally, also the results showed that interpretable models got a very similar performance results with black box models. So NASA or logistic regression is the preferred model for this study because they have good performance and easy model interpretability, simple, fast, and consistent with the data processing and the feature selection. So finally, do visualization reports. So this visualization, and this is, we can say, this is predict the probability. So this is the length of stay more than 4 hours, length of stay less than 4 hours. So most length of stay more than 4 hours predict much higher probability. The correlation, odds ratio on both sides of cutoff is 33, so it's pretty high. Let's say this one. This is a predict binary length of stay. At 10 minutes, the AUC is almost 0.9, and sensitivity and the precision so was very good. Accuracy is this one. And 1 hour and 2 hours, we can say very similar, not much difference. And this is the coefficient table. So selected features, coefficient, odds ratio. Because all data are standardized, so the standard deviation is 1. Adjusted, so the odds ratio adjusted was the same. This is an example to predict the binary length of stay using NASA regression at 120 minutes for ED visit. So this is raw data. So for a patient, this is raw data that selected features. And after data processing, so we convert all this into these numbers. Then we use this formula to calculate the predicted probability is 0.94. So this patient is very, very likely to stay more than 4 hours. So let's see the summary of this data analysis. We build models to support ED disposition decisions, 12 models with 21 features, each model with 21 features to predict 4 outcomes at 3 different time points. Similar performances at 3 different time points. So even at 10 minutes after triage, the model works very well. AUC for binary length of stay and the length of disposition decision is about 0.9. Accuracy for trinary length of stay and the trinary DD are not very good. In 3-class prediction is not as good as a binary prediction. And because we need the interpretable models, so the data processing are very important. So for categorical data processing, numerical data processing, we use some new method. The categorical data processing is like a target coding. The numerical data analysis is a new method. And we found some important features which affect ED disposition decisions. Some important points have been learned. So for this data analysis with real-world data, most time, more than 80% of time, are used for data processing. I mean, data extraction, create dictionaries, data preprocessing, data processing. Most time are for this. And secondly, some factors deemed important by domain experts like pulse and systolic BP not necessarily be considered as important by machine learning models. For machine learning models, those models try to select best indicators. Unfortunately, these two are not selected. And I checked very carefully, still not selected. So it's a little different from domain experts' ideas. And the feature average waiting time ranked among the top 10 features for all three models predicting binary length of stay, but not significant for any model predicting binary disposition decision. So this suggests waiting time influence a patient's length of stay, but does not impact the disposition decision made by clinicians. So, which means the doctors made the decisions, and this decision not influenced, even the emergency department very crowded, so these decisions are still carefully made, not influenced by the crowding. The first one, models predict binary length of stay and DD at 120 minutes post-triage shared 8 out of 10 top features. So this indicates a natural association between length of stay and disposition decision. In simple terms, after accounting for variation in waiting time, a patient whose care is completed within 4 hours might be best discharged directly from ED. One who requires 4 to 24 hours care might be well suited a short stay unit, and one needing over 24 hours of care may be best served as an inpatient on an inpatient ward. So length of stay and the disposition decision very close related, but that's important differences is waiting time. So for future work, so first, some important features are not used, like ICD-10 code. It has more than 87,000 categorical values. Triage comments is a free text feature. And the medications, it also has many categorical values, and it's not standardized. But all these features are very important. So in future, if we have good ways to process these features, the performance should be improved. Secondly, currently we use a different way to process the missing values, but for large complexity data set, if we can find a better way to impute missing values, the performance may be improved as well. And also for trinary outcomes, the performance are not very good. So in future should be improved. Also, some other studies can be done with the data set, like we can predict the triage categorical results. Even when the patient comes, we can do some predictions for some initial prediction. Yeah. So that's it. Thank you very much.